Hello there and welcome to Just About Earth, the place where wonder winds down and science wears slippers. Tonight we're sliding gently into one of the coldest mysteries our planet has ever kept. An ancient secret wrapped not in riddles, but in ice. For over 100 million years the Earth was locked in a deep freeze, not just a chilly winter or a frosty season, but a planet-wide stillness, where glaciers crept to the equator and even the seas froze over. Imagine that. A world so cold, the oceans turned to glass and the sky held its breath. But before we tiptoe back into that frozen chapter of Earth's history, can I ask, where are you listening from tonight? And what's the weather like on your corner of the planet? Is it snowing? Raining? Maybe the air feels warm on your skin, or maybe you're bundled up just as our ancestors once were, though hopefully with better socks. If you find this kind of journey comforting, or curious, or just a welcome way to soften the edges of the day, it would mean a great deal if you'd like this video or maybe subscribe. It helps others find their way here too, to this little nook of calm, where sleep meets science and the universe unfolds one quiet thought at a time. So settle in, slow your breath. The day is done, and now it's just you, this voice, and a question older than ice itself. Because somewhere in the archives of our planet's past there was an age so strange, so severe, that scientists once wondered if life could have survived at all. But it did. And tonight, we're going to find out how. This is the story of Snowball Earth. An ancient time when the world was so completely frozen over, it became almost unrecognizable. Glaciers at the equator, ice hundreds of meters thick, and yet, somewhere, somehow, life endured. How did it happen? What could possibly chill an entire planet for 100 million years? And just as importantly, what brought the warmth back? The story of Snowball Earth doesn't begin with glaciers or fossils or even theories. It starts with a compass. Or rather, with a compass that wasn't quite behaving. Sometime in the 1960s, a group of geologists were doing what geologists often do, chipping at rocks in places no one really vacations to. This time they were in the far north of Australia, where ancient stone outcrops had lain quietly for hundreds of millions of years, tucked beneath layers of dust, waiting. What they found there didn't make sense. Rocks that had clearly formed in tropical environments, fine laminated sediments usually laid down by shallow warm water, were magnetized in a way that said something very different. They were tilted, misaligned. The iron minerals inside them, tiny geological compass needles frozen in time, pointed not toward the ancient tropics, but toward the poles. To anyone else, it might have just looked like a glitch, a fluke. But to scientists it was a breadcrumb, one that led to a question so outlandish it bordered on science fiction. What if these rocks really had formed near the equator? And what if the Earth at that time had been frozen from pole to pole? It didn't stop there. Across the globe, similar signs began turning up. In Africa, Canada, China. Glacial sediments where no glacier should have ever reached. Dropstones. Large pebbles carried by icebergs and released into fine mud as the ice melted. Found in what were once tropical seas. Suddenly, the evidence was no longer subtle. It was everywhere. Like the Earth had once been wrapped in a thick shell of ice, an entire planet hibernating. Scientists started giving this idea a name, Snowball Earth. Not a metaphor, but a literal proposal that the planet, hundreds of millions of years ago, had been frozen over so thoroughly that even the oceans were capped with thick ice. Not just around the poles, but all the way to the equator. No open seas, no rainforest, no gentle tides lapping against a sunlit beach. Just white, white, in every direction. But how could that be? How could a planet that now swings between beach weather and blizzards have once become so utterly stuck in cold? And even more baffling, how could it ever come back from that? To understand this, we have to look not at the ice itself, but at the way scientists uncovered it. and the picture they built slowly, piece by piece, like reconstructing a dream from forgotten fragments. The compass needles were just the beginning. Geologists began looking deeper, at the chemistry of the rocks, the isotopes inside them, the layers upon layers of sediment left behind like pages in a forgotten book. One clue led to another. Isotopic signatures, ratios of carbon and oxygen, told a tale of wild climate swings. The types of minerals present hinted at frozen conditions. But the biggest revelations came from an unexpected place. Namibia. In the Namib Desert, where the air is dry and the ground crumbles underfoot, there's a rocky formation called the Otavi Group. It stretches for hundreds of kilometres, and in some places it holds something incredible. A thick band of glacial deposits, rocks and boulders dropped by ancient ice, directly overlain by something completely different. A sudden, sharp transition, from cold to carbonate. You see, carbonate rocks, like limestone, usually form in warm, shallow marine waters. Their presence right above glacial till suggests something dramatic happened. A rapid shift. A planet emerging from a long, deep freeze into something warmer. Suddenly, perhaps even violently. It was like finding a snowdrift beneath a tropical reef. And it wasn't just in Namibia. This exact same cap carbonate layer appeared in many parts of the world. Always the same story. Glacial debris, followed by signs of warmth. It painted a haunting picture. The Earth had not only frozen, it had thawed in a rush. But we're getting ahead of ourselves. Before the thaw, there was the freeze. And the road to that frozen state likely began long before the ice took hold. A team of researchers, including Paul Hoffman from Harvard and Daniel Schrag, began to piece together the global puzzle in the late 1990s. They weren't the first to suspect a global glaciation, but they brought something new, a model, a mechanism, and a willingness to entertain the improbable. Their work drew attention to the Sturtian and Marinoan glaciations, two massive ice ages that occurred roughly 720 and 635 million years ago, during a period known as the Cryogenian, which, fittingly, means cold birth. It was a time when continents were drifting, the atmosphere was shifting, and life, such as it was, clung to the oceans in microscopic films. There were no trees, no birds, no mammals. The land was bare, wind-scoured. The seas were home mostly to single-celled organisms and strange soft-bodied creatures. It was a quiet world, and then it grew quieter. The magnetic data, the glacial deposits, the cap carbonates, they all told a unified story. And that story was beginning to echo through the scientific community. The Earth, it seemed, had a memory of a time when the light grew dim, the temperature dropped, and the planet folded into itself like a snow-covered lantern. But memory, especially planetary memory, is complex. The rocks don't speak plainly. They whisper. They hint. They hold on to clues in the way a frozen lake might keep secrets beneath its surface. There's a rock formation in Canada's Mackenzie Mountains, nearly a kilometre thick, made entirely of glacial sediments from this era. In Svalbard, Norway, ancient tillites, compacted glacial debris, preserve the scouring marks of vanished ice. In China, dropstones lie scattered in layers that once formed the bed of a shallow sea. It was everywhere, not just cold, catastrophically cold. Still, not everyone agreed. Early critics of the Snowball Earth hypothesis argued it was too extreme. After all, a fully frozen ocean would trap sunlight. The planet would reflect nearly all incoming solar radiation back into space, and the cold would feed on itself, a runaway refrigerator with no off switch. If Earth had ever become that frozen, they said, how could it ever warm up again? But maybe that was the point. Maybe the very extremity of the event was the key. And maybe the Earth had a way, not a graceful one, but a powerful one, of breaking the cycle. But before we can warm it back up, we must understand what cooled it down in the first place. And for that, we need to look not just at rocks and compasses, but at a planet always balancing on the edge of change. A place where light, chemistry, biology, and even volcanoes play roles in an endless, intricate dance. A dance that, at least once in its history, led the world into stillness. Before the world froze, it was already changing. Not quickly, not in a flash, but in slow, creeping motions. The kind you only see when you step back far enough that entire mountain ranges become brushstrokes, and oceans shift like ink in a great unfolding map. Let's imagine Earth as it was around 750 million years ago in the late Proterozoic era. It was still a young planet, only a little over 3 billion years into its 4.5 billion year life. But even then it had already survived chaos. The crust had cooled, oceans had formed, life in its simplest forms had taken hold. Tiny, determined, quiet, mostly bacteria, mostly floating. Above the waves, the landscape would have looked almost alien to us. There were no trees, no flowers, no birds. The land was bare, ancient stone shaped by erosion, volcanic activity, and the tireless grinding of wind. Rivers meandered across empty plains. The skies held no bird song, only clouds shifting across the blue. If you were to walk this earth, you'd hear nothing but wind and water, maybe the distant hiss of volcanic vents, and beneath your feet, the crunch of dust older than memory. Yet beneath the silence, life was stirring. In the oceans, single-celled organisms had begun experimenting with something extraordinary. Cooperation. Some were forming colonies, others were developing internal complexity. The ancestors of plants, animals, and fungi all drifted in the sea like specks of possibility. The first steps toward multicellularity, arguably the most ambitious biological leap since life began, were just beginning to take hold. They didn't know what was coming. No one did. How could they? The continents were moving too, slowly, ceaselessly. Over millions of years, massive land masses had begun clumping together into a supercontinent scientist called Rodinia. Its name means to give birth in Russian, and in some ways, it did. Rodinia wasn't the first supercontinent, nor would it be the last. But its formation was critical, because the way it clustered land together, its position near the equator, its exposure to weathering, may have helped tip the scales toward catastrophe. When continents form near the tropics, something interesting happens. Warm, moist air fuels heavy rainfall, and that rain erodes exposed rock. That might not sound dramatic, but chemically it is. Because the breakdown of silicate rocks during weathering pulls carbon dioxide out of the atmosphere. The carbon doesn't vanish, it gets washed into the sea, locked away in sediments. This process over long spans of time acts like a planetary thermostat. More weathering means more CO2 removal, and less CO2 in the atmosphere means less of the greenhouse effect, less heat. As Rodinia eroded slowly and constantly, it began to scrub the sky clean. The planet cooled, bit by bit, degree by degree. And though volcanic eruptions still added some CO2 back, the balance began to tip. Over hundreds of thousands, even millions of years, the atmosphere thinned of its warming gases. And then something shifted. Scientists still debate what the final trigger was. Maybe it was the continued weathering. Maybe the sun itself, which at the time was about 6% dimmer than it is today, simply wasn't warm enough to compensate. Maybe a feedback loop began, one that Earth had no easy way out of. The ice began to spread. At first it crept slowly, glaciers forming in the highlands, at the poles, in the shadows of the supercontinent. But ice, like curiosity, is rarely content to stay still. As it expanded, it increased the planet's albedo, its reflectivity. Snow and ice reflect sunlight far more effectively than rock or water. More reflection meant less heat absorbed. Less heat meant more cooling, and more cooling meant more ice. A feedback loop had begun, a dangerous one. Eventually the ice reached the oceans. It didn't stop. Ice rafts floated through tropical seas. Glaciers carved their way across equatorial landscapes, and still the ice deepened. The temperature plunged. The oceans themselves began to freeze, not just at the surface, but potentially down hundreds of meters, perhaps even to the seafloor in places. No open water, no gentle waves, just a world locked in white. Scientists estimate that surface temperatures may have dropped to 50 degrees in many regions. The tropics, places we now associate with lush forests and bright sun, may have hovered just below freezing, enough to sustain ice year-round. Even the air would have changed, dry, sharp, still, and yet it was not a dead world. Beneath the ice, something persisted. The oceans didn't freeze solid, not entirely. Geothermal heat from within the Earth likely kept the deep oceans liquid. Volcanic activity on the seafloor bubbled and fumed, releasing warmth and nutrients. In the dark, microbial life held on. Some scientists imagine pockets of open water near volcanic islands, rare and temporary. Others propose thin zones beneath the ice where photosynthesis could still occur, perhaps aided by translucent ice or cracks that let in just enough light. Extremophils, organisms that thrive in harsh environments, may have found refuge around hydrothermal vents, as they still do today. Life didn't flourish. It didn't thrive, but it survived. In fact, some believe this crucible of ice may have played a role in shaping the future of life itself. Stress and scarcity can be powerful drivers of innovation. The long, deep freeze may have acted as a bottleneck, squeezing populations down, selecting for resilience, cooperation, adaptability. When the thaw came, and it would come, life was ready to bloom again, stronger and stranger than before. But for tens of millions of years, perhaps more than 100, Earth stayed frozen. The silence held. The glaciers persisted. And from space, our world must have looked like a pale marble, quiet, cold, and suspended in an ancient slumber. Today, we find traces of that time in the scars it left behind. Glacial striations carved into bedrock, erratic boulders dropped far from their origin, chemical signatures locked in ancient minerals. Even the cap carbonates, laid down after the thaw, tell a tale of oceans gone suddenly blue again, flooded with warmth and carbon. And we ask ourselves, how did it last so long? And just as haunting, how did it end? We'll get there. But before that warming began, before the feedback loops reversed and volcanoes belched enough carbon to tilt the balance again, there was only the deep, the dark, the hum of a planet dreaming beneath its icy shell. And if you listen, even now, in the wind sweeping across Antarctica, in the crunch of glacier underfoot, in the ancient pulse of deep-sea vents, you can almost hear it still. In stories, there's often a single moment when everything changes. A match struck, a curtain drawn, a single pebble setting off an avalanche. But the Earth doesn't usually work like that. Its great shifts and turns are rarely sudden. Instead, they unfold in layers, in sequences, a kind of deep geological choreography where one step leads slowly into the next. And yet, sometimes, something happens that tilts the balance. To understand why the Earth froze so completely, we need to look at more than just cold. Cold, after all, is a symptom, a surface-level echo of deeper causes. What matters is how the planet lost its grip on warmth, and how feedback loops, both biological and geological, set a runaway freeze into motion. It starts with the sun, a quiet player, but an essential one. Back during the Cryogenian period, the sun was fainter than it is today, perhaps 6 to 7% less luminous. Now that might not sound like much, but even a small dip in solar input can have profound consequences for global temperatures. The Earth wasn't being warmed as efficiently as it is now. It was skating, in a way, along the edge of stability. Then came the continents. As we saw, the formation of Rodinia placed massive land masses near the equator, where warm, humid air and heavy rains erode rocks quickly. This process, called chemical weathering, pulls carbon dioxide out of the atmosphere. Specifically, it locks CO2 into carbonate minerals and sediments, removing it from the sky and burying it in stone. CO2, of course, is a greenhouse gas. It traps heat. So when you remove it, things start to cool, and if you remove enough, the thermostat drops dramatically. The Earth becomes more reflective as ice spreads, which reflects even more sunlight, which causes more cooling, and so the cycle begins. This is what scientists call a positive feedback loop, though it feels anything but positive. More ice leads to more cooling, leads to more ice. It's self-sustaining, and if nothing interrupts it, it can spiral out of control. But there's another player here, a quiet, slippery molecule with an outsized impact: methane. Methane is a greenhouse gas too, far more potent than CO2, though it doesn't last as long in the atmosphere. It's produced naturally, often by microorganisms called methanogens. These microbes thrived in Earth's early oceans and wetlands, bubbling out methane as a waste product. For a long time, methane helped keep the Earth warm. But then, oxygen began to rise. This rise didn't happen overnight either. It was part of a long, complex transition known as the Great Oxidation Event, which had started over 1 billion years earlier, but continued through the Proterozoic. As oxygen levels crept up, it began reacting with methane in the atmosphere, breaking it down into CO2 and water vapour, less potent greenhouse gases. With less methane in the sky and more CO2 being scrubbed away by weathering, the Earth's greenhouse blanket began to thin. Less insulation, more exposure, more vulnerability to cooling. Volcanoes were still active, of course, they always are, and they constantly add CO2 to the atmosphere. Under normal conditions, this volcanic input balances out the removal of carbon by weathering. But if the balance tips, if weathering outpaces volcanic outgassing, the carbon levels fall, the planet cools, and the ice begins to creep. And so, somewhere between 750 and 720 million years ago, the stage was set. A dimmer sun, equatorial continents weathering aggressively, a loss of atmospheric methane, volcanic CO2 not quite keeping up. The climate slipped, the poles grew colder, snow began to accumulate that never fully melted. Glaciers thickened, and the albedo loop clicked into place. Once ice reached about 30 degrees latitude, a line somewhere around present-day Florida or northern Egypt, scientists believe the feedback became unstoppable. From there, it only took a few thousand years for the rest of the planet to lock up. In geological terms, that's lightning fast. A blink. The blink of a snowstorm. The oceans, once teeming with microbes and simple eukaryotes, began to seal beneath thick caps of ice. These weren't delicate sheets either. Some estimates suggest sea ice may have reached hundreds of meters thick, even in the tropics, and beneath that cap sunlight all but vanished. Photosynthesis slowed, perhaps even halted in places. The oceans grew still, stratified, starved of oxygen. Ecosystems collapsed, and yet some forms of life clung on. Microbial mats, extremophils huddled near hydrothermal vents. Perhaps a few rare algae survived in brine channels or thin layers beneath translucent ice. It wasn't thriving, but it was living. And life, as Earth would prove again and again, has a habit of enduring the impossible. For tens of millions of years, this deep freeze continued. The Earth was caught in a feedback loop with no easy exit. Temperatures hovered around 40 degrees or colder in many regions. The oceans were locked in. Rainfall nearly ceased. The hydrological cycle slowed to a crawl. And yet, even in this silence, something was building. Something unseen. Something patient. You see, the very thing that had failed to prevent the Ice Age, volcanism, was still quietly working beneath the surface. Volcanoes don't stop just because the surface is frozen. In fact, beneath kilometres of ice, magma still rose. Mid-ocean ridges still pulsed with heat. Continental rift zones still oozed basalt, and every eruption released CO2. But here's the catch. During Snowball Earth, with the ocean sealed off and the land buried under ice, the planet's usual carbon sinks, the places where CO2 gets absorbed, weren't working very well. Weathering had mostly stopped. There were no rainstorms to wash carbon into rivers, no exposed soil to react with minerals. The geological scrubbers were offline, so the CO2 began to build, slowly, steadily, year by year, eruption by eruption. It accumulated in the atmosphere, and without a place to go, the levels rose, higher than they had been in hundreds of millions of years. It was like a pressure cooker with the lid sealed tight. Eventually, this greenhouse blanket began to take effect. The ice reflected most sunlight, yes, but CO2 traps heat in the infrared range, radiation bouncing off the Earth's surface, and once there was enough of it, the balance tipped again. The deep freeze didn't end all at once, but it ended fast, geologically speaking. Climate models suggest that once CO2 passed a certain threshold, possibly over 100 times modern levels, the greenhouse effect surged. The planet began to thaw, ice retreated, glaciers cracked, the oceans, long sealed, began to breathe again, and when they did, something extraordinary happened. Remember those cap carbonates? The strange layers of tropical rock lay directly on top of glacial debris? They formed in this moment. As the ice melted, immense amounts of CO2 remained in the atmosphere and ocean. The sudden influx of light and heat triggered rapid chemical reactions. Carbonates precipitated out of the water, blanketing the seafloor in layers of rock that today serve as signposts of the thaw. The Earth, once a frozen marble, returned to blue. But the story doesn't end with the melt. In fact, in some ways, it was just beginning. Because this was not just a climate event, it was a reset button. Ecosystems had been levelled, atmospheric chemistry had shifted, and life, clinging by a thread for millions of years, now had a chance to reinvent itself. Oxygen levels began to rise again. Weathering resumed. Rivers carved new paths through newly exposed landscapes, and in the oceans the survivors, those tiny, stubborn life forms, began to diversify. Many scientists believe that the end of Snowball Earth helped pave the way for one of the most extraordinary chapters in life's history, the rise of complex multicellular organisms. In the millions of years that followed, strange forms began to appear in the fossil record. The Ediacaran biota, soft-bodied, otherworldly creatures with no clear modern relatives, drifted across seafloors and anchored to sediment. They didn't leave much behind, just faint impressions in ancient mudstone, but they hint at something profound. A world waking up. Life, after surviving the edge of extinction, beginning to explore complexity. The snowball events didn't cause this directly. They weren't some magical trigger, but they cleared the board. They set new rules. And in the quiet warmth that followed the melt, life seized the opportunity. From there, the clock ticks forward, slowly at first, then faster. By 540 million years ago, the Cambrian explosion would burst forth, populating the seas with trilobites, worms, early vertebrates, and the ancestors of nearly every major animal group alive today. But deep beneath that evolutionary bloom is the memory of the freeze, the scars it left, the silence it imposed, and the fragile threads of survival that carried life across 100 million frozen years. So what triggered Snowball Earth? 1,000 small changes, layered like sediment, a dimming sun, the slow drift of continents, the breath of microbes, the slow exhale of volcanoes, and once set in motion, it was the planet's own feedbacks that pushed it deeper, harder, colder, until eventually the Earth found its way back, not because it planned to, not because it wanted to, but because even a frozen world can only hold its breath for so long. When the world begins to thaw after 100 million years of ice, it doesn't simply return to normal. It transforms, dramatically, violently, and forever. Imagine this. Thick ice sheets stretching from pole to equator, melting not over eons but in a geological heartbeat. Glacial walls collapse, rivers reawaken, oceans rise. The soundscape of the planet, once muffled and muted, erupts with motion. Not birdsong, not animals, but the deep creak and crack of ancient ice giving way, the hiss of steam where sun touches permafrost, the thunder of landslides reshaping coastlines that hadn't seen open air in millennia. But beneath this theatrical curtain rise is something even more powerful, an invisible chain of chemical reactions. As the glaciers retreat, they do more than release water. They expose rock, bare, weathered stone that hasn't seen the sky in millions of years. And with exposure comes reaction. Water meets minerals, sunlight meets nutrients, and suddenly the planet's slow breath begins again. This new breath is rich in carbon. The long volcanic exhale of the Snowball period left CO2 levels staggeringly high. Models suggest atmospheric carbon dioxide may have climbed past 10,000 parts per million, over 25 times modern levels. And with no plants to pull it back yet, it lingered, thickening the air like a woolen blanket draped over a recovering patient. The result: heat. Intense global transformative heat. It didn't just melt the remaining glaciers, it supercharged the planet's climate system. Rains returned with force, carving channels through freshly exposed sediments. Monsoons may have battered tropical regions, and into this turbulent world, nutrients poured. As the glaciers scraped across continents, they pulverized rock into fine, mineral-rich dust. When that dust washed into the sea, it acted like fertilizer. Phosphorus, iron, and other key elements flooded the upper ocean, where sunlight now reached again. And the microbes, the ancient survivors of the deep, responded. Phytoplankton bloomed. Simple algae, dormant or diminished during the freeze, exploded in number. They feasted on the nutrients, photosynthesized furiously, and in the process began transforming the atmosphere once again. For every pulse of sunlight they captured, they released oxygen. And as populations grew, so did their impact. This is one of the paradoxes of Snowball Earth, that a planet nearly sterilized by ice might come back greener, richer, and more alive than before. But the revival wasn't smooth. It came with consequences, sharp, destabilizing ones. As oxygen levels rose, they began to interact with a newly oxygen-starved ocean. During the Snowball period, much of the ocean had gone anoxic, depleted of oxygen. This happens when water becomes stratified. Cold, dense water below, with no mixing, no churn. Microbes adapted to the deep had taken over, some producing hydrogen sulfide, a toxic gas. When the ice melted and surface circulation resumed, these deep waters began to rise, and they carried their chemistry with them. In what some scientists describe as a toxic reflux, large amounts of hydrogen sulfide may have been released into shallow waters and even the atmosphere. The result would have been lethal for many newly recovering organisms. This kind of event is known as euxenia, and there's evidence from sulfur isotopes and ancient sediments that it may have happened several times in Earth's history, including just after Snowball Earth ended. So just as life began to rebound, it may have been knocked back down again. But each time, something survived. And each time, the survivors built a little more complexity. One by one, the feedback loops began to reverse. Weathering of newly exposed rock began to draw CO2 back down. The carbon that had built up over millions of volcanic years was slowly washed into the sea, stored once more in sediment. Atmospheric temperatures began to cool, gently, gradually. The wild swings of Snowball Earth gave way to something more stable, and in that relative calm, ecosystems began to reweave themselves. The oceans became productive, oxygen levels stabilized, carbon cycles resumed their slow dance. And with environmental pressures easing, biology got creative. Cells began forming new partnerships. Some banded together, others specialized, and slowly, through processes still only partially understood, multicellularity began to flourish. Some scientists believe the Snowball episodes acted as an evolutionary crucible, a filter. They didn't directly invent new life forms, but they created the space and pressure for innovation. And after each global freeze, we see hints of something new in the fossil record. New shapes, new strategies, new life. But Earth doesn't forget what it's been through. Even after the glaciers melt and forests return, the scars of deep time remain etched into its bones. In Namibia, the Otavi group still holds the mark of sudden warming, the cap carbonates lying like white linen atop glacial rubble. In the Canadian Shield, striations carved by ancient ice remain sharp enough to trace with a fingertip. In China's Yangtze Gorge, dropstones, evidence of drifting icebergs, interrupt layers of fine sediment, like punctuation in a long-forgotten sentence. And then there's the chemical record. Carbon isotopes, particularly the ratio of carbon-13 to carbon-12, show dramatic swings before, during and after the cryogenian glaciations. These ratios reflect how much organic carbon was buried, how active photosynthesis was, how much life the planet could support. During snowball events, the signal drops sharply. Less carbon burial, less biological activity. But after the thaw, the ratios rebound, sometimes violently. The biosphere lurches back to life. Sulfur isotopes tell a similar story. They track the behaviour of microbial sulfur metabolism, key to understanding anoxic and euxenic conditions. Shifts in these values suggest that after Snowball Earth, the ocean chemistry went through spasms. Layers of life and death, bursts of oxygen, crashes of toxicity. It wasn't smooth, it wasn't gentle, but it was transition, and through it all life kept climbing. Perhaps it's worth pausing here to sit in the strangeness of it all, to remember that this isn't myth, this isn't allegory, this happened. Our planet, the one beneath your feet, the one whose gravity pulls your breath downward as you fall asleep, once froze so deeply that the equator itself were a glacier. And yet, here we are. So what's the takeaway from all this icy turmoil? What are the aftershocks of a 100-million-year freeze? Some are planetary. The Snowball episodes reshaped the carbon cycle, altered the trajectory of Earth's atmosphere, and set the stage for more stable climate regimes. They may have helped establish the balance we now enjoy. Just enough greenhouse warming to avoid another deep freeze, just enough weathering to prevent runaway heating. Others are biological. After Snowball Earth came the Ediacaran period, a time of experimentation. The fossil record begins to show large multicellular forms with strange body plans, quilted discs, tubular creatures, frond-like stalks. Not quite animals as we know them, but certainly a step beyond microbes. They hint at a biosphere finding its footing again, testing new blueprints. Still others are philosophical, because Snowball Earth reminds us that stability is not the default. Our climate, our ecosystems, even life itself, they are the product of balance, not certainty. And balance can be tipped, not easily, not instantly, but gradually, through slow, unseen changes, through feedbacks we might not even notice until it's too late. It also reminds us that recovery is possible, that resilience is buried deep, not just in biology, but in the planet itself. That after unimaginable stillness, there can still be motion, and life, and heat. And for those of us living now in a time of rising CO2 and melting ice, that's a strange comfort and a gentle warning. Because while Snowball Earth was a natural event born of ancient tectonics and long-term cycles, it teaches us how profoundly sensitive the planet can be, how climate can swing, not just by degrees but by epochs, how feedback loops can spiral both into silence and into song, and that lesson, that might be more important now than ever. The Earth, as strange as it seems, has done this before. Not the exact same freeze, not the same feedback loops, not the same creatures huddling beneath the ice, but the pattern, the rise and fall, the long inhale of heat, followed by the slow, freezing exhale. Extinction, recovery, innovation, and silence. Snowball Earth was not the first great transformation this planet endured, and it would not be the last. Long before the world turned to ice, it had already been reshaped by a different kind of storm, one made not of snow, but of air. Rewind the clock more than 2 billion years, and you reach the Great Oxidation Event, a time when tiny photosynthetic microbes, called cyanobacteria, began exhaling oxygen in quantities the planet had never seen before. What they released as waste would become the foundation of everything we now breathe. But at the time, it was chaos. Oxygen, for all its life-giving beauty, is also reactive. It rusts iron. It kills anaerobic life, and as it flooded the atmosphere, it sparked a planetary crisis. Methane, which had kept the Earth warm under a fainter sun, was broken down. Temperatures dropped, ecosystems changed, and some scientists suspect that this shift may have triggered one of Earth's earliest and most forgotten ice ages. It's called the Huronian glaciation, and it may have lasted for hundreds of millions of years. It was a different world back then, one with far fewer continents, far less land life, and a very different kind of sun. But even in that primordial era, the same forces were at play: greenhouse gases rising and falling, biological feedback loops altering the atmosphere. Earth doesn't repeat itself exactly, but it rhymes. And if we jump forward again, past the Cryogenian, past the strange organisms of the Ediacaran, into the Phanerozoic Eon, the time of visible life, we find a new rhythm. The tempo quickens. Extinction and evolution dance closer together. The great freezes are replaced occasionally by great burnings, heat waves, firestorms, poisonous seas. One of the most famous extinction events, of course, is the one that ended the age of dinosaurs, caused by a massive asteroid impact 66 million years ago. But even that sudden cataclysm echoes deeper processes we've already seen. The impact sent dust and aerosols into the atmosphere, reflecting sunlight, dropping temperatures, triggering a kind of nuclear winter. Plants died, food chains collapsed, and only the adaptable survived. Once again, the cooling wasn't just a backdrop, it was a key player. Before that came the Permian-Triassic extinction, sometimes called the Great Dying. 252 million years ago, over 90% of marine species and 70% of terrestrial vertebrates vanished. The causes are still debated, but one major suspect is volcanic activity. Massive eruptions in what is now Siberia that flooded the atmosphere with CO2 and sulfur, acidifying the oceans and triggering climate chaos. Extreme warming followed by ocean stagnation and mass die-offs. It's the opposite of Snowball Earth in terms of temperature, but strikingly similar in structure. A trigger, a cascade, a rebalancing, and a new world left in the aftermath. What all these events share is not their shape, but their rhythm. Earth shifts, it tips, it pulses between extremes, and each time life is pressed to its limits, sometimes crushed, sometimes reborn. The Snowball episodes of the Cryogenian are just one verse in this long poem of planetary change, but they stand out for their severity and their timing. Because when the world froze over 720 million years ago, life was still simple, fragile, experimental. It hadn't yet exploded into animals or trees or fish or feathers, and yet it endured. Some scientists believe these deep freezes helped prepare the biosphere for the complexity that would follow. It's a bold idea, but not a ridiculous one. Extreme stress can lead to rapid innovation. Populations forced into small isolated pockets often evolve quickly. Competition sharpens, cooperation increases, genetic pathways open under pressure that would otherwise remain dormant. It's no coincidence, perhaps, that after the last Snowball event, we begin to see the earliest hints of what might become animals. Soft-bodied forms drifting across the ocean floor, leaving faint impressions in the sediment, ghostly blueprints of a future world. But to understand the scale of Snowball Earth and its uniqueness, we also have to look at what didn't happen again. After the Marinoan glaciation ended roughly 635 million years ago, there were no further full planet freezes. Ice ages, yes. Cold snaps, certainly. But not the kind that wrapped the entire globe in silence. Not the kind that touched the tropics and strangled the sea. Something had shifted. Many scientists believe it was the Earth's evolving carbon cycle. Specifically, the emergence of land plants hundreds of millions of years later that began to regulate the planet more tightly. Plants, with their roots and their leaves, act as carbon pumps. They pull CO2 from the sky, store it in tissues, lock it in soils. They modulate climate in ways that earlier ecosystems simply couldn't. Tectonics played a role too. The arrangement of continents affects ocean currents, weather patterns, and the distribution of ice. After Rodinia broke apart, new supercontinents rose and fell, Gondwana, Pangaea, Laurasia, all shifting the balance differently. Earth, it seems, grew better at preventing the kind of total freeze it had once endured. But the possibility never went away, and the memory remained, in rocks, in isotopes, in the very genes of the creatures that survived it. Perhaps the most beautiful thing about studying Snowball Earth is not just what it tells us about the past, but what it suggests about life's relationship with catastrophe. We often imagine extinction as the end of the story, but sometimes it's a turning point. A hard, merciless one, but a turning point nonetheless. Before Snowball Earth, life had been content to float, to drift, to remain small. Afterward, it began to climb, not immediately, not inevitably, but steadily. With each extinction, each recovery, each rebalancing of Earth's chemistry and temperature, the biosphere stepped further into complexity, until eventually it gave rise to coral reefs, to forests, to wings, to thought. And while the Snowball episodes weren't the only cause of that journey, they were among the most profound crucibles it ever passed through. They remind us that Earth is not a static world, that the conditions we take for granted, temperate seasons, breathable air, open oceans, are not permanent settings. They are negotiated balances, held together by invisible threads of geology and biology and sunlight. They remind us too that crisis does not always mean collapse, that under ice, in darkness, without sun or surface, life finds a way. And when the thaw comes, however late, however violent, it often rises stranger, stronger, and more astonishing than before. From the ancient bacteria that built oxygen into our skies, to the microbes that withstood the cold, to the soft-bodied forms that crept across post-glacial seas, each carried the memory of catastrophe, not as a burden, but as a blueprint. And maybe, just maybe, we carry it too. When the Earth froze over 700 million years ago, no one was watching. No one was there to record it, to sketch the first ice creeping toward the equator, to listen for the silence as the last wave stilled beneath the cap of sea ice. There were no eyes to see, no ears to hear, no stories told. But stories eventually would come, and they would begin not in frozen oceans, but in deserts, in mountains, in rocky ridges split open by time and curiosity. Because if Earth keeps its memories in stone, then it was only a matter of time before someone began learning how to read them. The human story of Snowball Earth doesn't begin with a grand theory. It begins with questions. Questions carved out by fieldwork, by serendipity, by people standing in the wind and squinting at rocks and wondering why something didn't fit. One of those people was Brian Harland, a geologist from Cambridge. In the 1960s, Harland was looking at glacial deposits in Svalbard, high in the Arctic Circle, when he realised something strange. The rocks he was studying looked like they'd been formed by glaciers, but the magnetic data, the orientation of iron minerals frozen in the stone, suggested they'd been near the equator when they formed. At first, this idea was treated with scepticism. It seemed absurd. Glaciers in the tropics? How could that be possible? Surely the data were wrong. Surely something had moved the rocks, twisted the signal, played tricks with ancient magnetism. But the data held, and Harland wasn't alone. In Australia, scientists found similar evidence. Glacial sediments lying near what had once been tropical zones. In Africa, in China, in Canada, the pattern repeated. It wasn't just one outcrop or one anomaly, it was global. The Earth had left behind a riddle, and suddenly people began to realise it was written in more than one language. The term Snowball Earth wouldn't be coined until decades later, but the pieces were already being gathered. Sedimentologists studied the textures of glacial tills, poorly sorted rocks jumbled together by ice. Paleomagnetists reconstructed continental positions based on the alignment of minerals in ancient lava flows. Geochemists analysed isotopes looking for the subtle fingerprints of climate catastrophe. Still, for a long time, the theory remained quiet. A curiosity. An odd idea whispered between colleagues filed under maybe. Then came Paul Hoffman, a Canadian geologist with a restless mind and a love for fieldwork. Hoffman had spent much of his career mapping rocks in Namibia. In the late 1980s and early 90s, he began to piece together a picture that would transform the quiet curiosity into a bold hypothesis. Namibia at the time wasn't the easiest place to work. The roads were rough, the field sites remote, but the rocks, the Otavi group, were spectacular, and what they showed was a stark transition. Thick layers of glacial deposits, full of drop stones and striated clasts, overlain abruptly by bright warm water carbonates. It was as if winter had slammed into summer without pause. Ice followed immediately by tropical seas. That transition was the key, and it was everywhere. The same signature appeared in Canada, in Svalbard, in Australia. Cap carbonates lying directly atop glacial sediments. Not just a local feature, but a global pattern. Hoffman joined forces with Daniel Schrag, a geochemist from Harvard, to test the idea. Together they developed a model. The world had frozen over entirely, the oceans sealed by thick ice, the planet reflecting most of its sunlight. And the only escape eventually was a build-up of volcanic CO2, thousands of times modern levels, leading to a rapid, dramatic greenhouse rebound. They published their work in the late 1990s, and suddenly the phrase Snowball Earth entered the scientific mainstream. It was a radical idea, still is, but it offered something rare, a unifying explanation for a wide swath of evidence: magnetic signatures, glacial tillites, isotopic anomalies, the curious structure of cap carbonates. It stitched the puzzle pieces into a story, and like all good stories, it provoked debate. Science, after all, thrives on disagreement, and Snowball Earth had no shortage of it. Some geologists argued that the glacial deposits didn't prove a full freeze. Maybe the continents had simply drifted closer to the poles than expected. Maybe the paleomagnetic data were misinterpreted. Maybe there had been large glaciers, but still open patches of ocean, a slush ball Earth, not a snowball. Cold? Yes, but not sealed shut. Others questioned the cap carbonates. Why would warm water deposits form so quickly after glaciation? Could they have been laid down over longer timescales? Were they really the product of a CO2 spike and rapid thaw? Hoffman and Schrag welcomed the criticism. They revised their models, refined their predictions. More fieldwork followed, more samples, more data. And slowly, a consensus began to form, not on every detail, but on the broad strokes. Something extraordinary had happened in the Cryogenian. The world had entered a deep global freeze, and life had somehow persisted. The mystery pulled in more minds. Joseph Kirschvink, a geobiologist at Caltech, helped clarify the paleomagnetic evidence and gave the theory its memorable name, Snowball Earth. Marty Kennedy studied the carbon and sulfur isotopes that showed strange shifts in ocean chemistry. Shuhai Xiao, a paleontologist in China, traced the earliest fossils of multicellular life in the aftermath of the glaciations. Each of these scientists worked a different thread, but together they wove a richer picture of Earth's deep history. Not a single event, but a tapestry of ice and recovery, catastrophe and reinvention. And like all scientific journeys, it wasn't just the theories that mattered, it was the people. Field notes smudged with desert dust, boots worn thin from weeks in the field, lab benches cluttered with thin sections, isotope graphs, half-finished mugs of tea, debates that stretched into the night, moments of doubt and then the quiet click of something making sense. Many of the most important discoveries came not in eureka flashes, but in the slow, careful work of people returning to the same rocks year after year, asking new questions each time. And behind all of it, the quiet persistence of curiosity. Because it takes a certain kind of mind to look at a boulder with a scratch on it and wonder if it once rode an iceberg through a tropical sea. To stand in the middle of the Namib Desert and imagine it buried beneath glaciers. To see not just what the world is, but what it once was. Snowball Earth is not just a story about ice. It's a story about human wonder, about the way we listen to stone, about the way we follow strange clues into deeper mysteries. It reminds us that science isn't just equations and labs, it's people, standing in the wind, chasing whispers from deep time. And in those whispers, we hear echoes not just of Earth's past, but of its potential futures. To truly understand Snowball Earth, not just as an idea, but as a living theory, you have to slip beneath the surface of the story. You have to step into the quiet rooms of laboratories and the frozen timelines of geochemistry. Because hidden beneath every dropstone, every cap carbonate, every strange fossil, is something even more delicate: the data. We'll begin with isotopes, nature's tiny clocks, memory shards embedded in stone. Carbon, for instance, comes in multiple forms. Most of it is carbon-12, light and stable, but some of it is carbon-13, just a little heavier. Life tends to prefer carbon-12, using it in photosynthesis and metabolic processes. So when lots of photosynthetic life is active, drawing in carbon, burying it in sediments, the ratio of carbon-13 to carbon-12 in the ocean and atmosphere shifts. By measuring these ratios in ancient rocks, scientists can infer what the biosphere was doing. During the Snowball Earth events, these ratios plummet. The signal fades, photosynthesis slows. The world isn't dead, but it's quiet, like a garden gone dormant. Then, at the end of the glaciation, the ratios swing wildly again, a signal that life is roaring back. This kind of analysis is called carbon isotope stratigraphy, and it's one of the most elegant tools geologists have. It's like reading a musical score, where the notes are chemical traces left behind by breathing oceans. There are others too. Sulfur isotopes tell a story about microbial metabolism, specifically the behavior of bacteria that use sulfur compounds instead of oxygen. During the frozen periods when the oceans became stratified and oxygen-starved, these bacteria thrived. Their fingerprints are found in the sulfur record, odd anomalies that suggest euxinic conditions, where hydrogen sulfide, a poisonous rotten egg gas, accumulated in the deep sea. And then there's strontium. This element enters the ocean through the weathering of continental rock. When glaciers scrape away topsoil and expose bedrock, weathering accelerates, and so does the strontium signal. Scientists have traced this spike to just after the Snowball events, when melting ice flooded rivers with minerals. A global detox. The Earth washing its face after 100 million year slumber. Each of these isotopic tools acts like a different lens. Together they offer a layered portrait of a world in flux, not just freezing and thawing, but breathing and responding. And then, of course, there's the matter of time itself. How do we know when these glaciations happened? How long they lasted? How quickly they ended? For that, we turn to radiometric dating, one of geology's most powerful timekeeping devices. Certain elements decay over time at a known steady rate. Uranium becomes lead, potassium becomes argon. By measuring the ratio between the parent and daughter isotopes in a rock, and knowing the half-life of the decay, scientists can calculate its age. Not just roughly, but often with a precision of within 1 million years. In the context of Snowball Earth, this is critical. It helps establish timelines. When the glaciation started, when it ended, how long it lasted, and it allows us to correlate rocks from different continents. If a glacial deposit in Namibia dates to the same period as one in Australia, and they both lie beneath the same kind of cap carbonate, it strengthens the case for a global event. And it wasn't just one event. The Cryogenian period hosted at least 2 major snowball episodes. The Sturcian, around 717 to 660 million years ago, and the Marinoan, from about 650 to 635 million years ago. Between them may have been a brief interglacial, a fragile warming, possibly incomplete. But the evidence suggests the freeze returned with full force. Some scientists even argue for a third, older glaciation, the Kaigas, but its extent remains debated. The lines blur. The further back we look, the more the pages curl at the edges. And yet, the story holds. Beneath the microscopes, in the cleanrooms of isotope labs, scientists tease apart the fine grains of this deep time novel. Not to prove a point, but to understand a rhythm, a pattern the Earth keeps playing. But there's more than chemistry, more than clocks. There's the question of climate modelling, of how we recreate such an alien world on digital canvases. In research centres around the world, scientists build simulations, mathematical Earth stitched together by equations. They feed in data, solar intensity, atmospheric composition, ocean currents, ice albedo. They try to find the tipping point, the threshold beyond which ice consumes the tropics, and they find it. Model after model shows that once ice reaches a certain latitude, around 30 degrees north or south, the feedback loop becomes irreversible. Sunlight reflects off snow. The planet cools further, the oceans begin to seal, the world slips under, but the models also show a way out. Seost, slowly built up through volcanic outgassing during the freeze, eventually thickens the atmosphere to the point where the greenhouse effect becomes overwhelming. The ice retreats, the feedback reverses, warmth floods back in, the models match the evidence, the physics agrees with the chemistry, and through them we see not just the what of Snowball Earth, but the how. Still, some of the deepest mysteries lie not in rocks or equations, but in biology. In the question of how life survived. Because if the oceans were sealed beneath thick ice, if sunlight vanished, if oxygen dropped and nutrients became scarce, how did anything endure? One answer lies in extremophils. Even today we find microbes thriving in places that resemble snowball conditions, under the Antarctic ice, in brine pockets too salty to freeze, near hydrothermal vents on the ocean floor, where superheated water gushes from cracks in the crust. In caves sealed from light for millions of years, these organisms make their own energy. They don't need sunlight. They survive on chemistry, on sulfur, iron, hydrogen. They show us that life doesn't need luxury, just persistence. Some scientists believe ancient microbial mats, layered communities of bacteria, clung to the undersides of sea ice, where light may still have penetrated. Others suggest that open water refugia might have existed near underwater volcanoes or along tectonic ridges, where the ice was thin or absent. There's even evidence of glacial refugia, patches of land or ocean that remained ice-free due to unique local conditions, thermal anomalies, elevation, geography. These pockets may have harboured small, isolated ecosystems, tiny arc worlds floating in a sea of cold. And there's another clue, one that only recently emerged. In the fossil record after the Marinoan thaw, we begin to see the rise of organisms that exhibit signs of multicellularity. Not just clumps of cells, but differentiated tissues, organized structures, complexity. Could it be that Snowball Earth didn't just spare life, but sculpted it? Stress, after all, is a powerful driver of evolution. When environments shift dramatically, when resources grow scarce, organisms must adapt or disappear. Those that can cooperate may outlast those that compete. Those that can specialize may find a new niche. Bottlenecks don't just cull, they clarify. And in the aftermath of Snowball Earth, we find hints of that clarification. In China's Dushantuo Formation, fossils show early animals, or perhaps their precursors, preserved in exquisite detail. Tiny embryos, complex cell divisions, possible sponges, all emerging in the shadow of the Great Melt. In Newfoundland and Australia, strange quilted organisms begin to appear, Ediacaran life. Not quite animals, but not entirely foreign either. They fill the sea floors with soft bodies and fractal forms, hinting at an experiment in form and function. And genetically, we can trace the timing. Molecular clock analyses, based on DNA mutation rates, suggest that many major lineages of animals began diverging around this time. Not during the Snowball episodes, perhaps, but shortly after. Once the world thawed, once the nutrients returned, once oxygen found its footing again, Snowball Earth, in this view, becomes more than a catastrophe. It becomes a stage, a bottleneck that narrows then opens, a crucible of dormancy, followed by riotous invention. This idea is still being tested, still debated. Some scientists argue that the link between glaciation and complexity is coincidence, that life was already on this path and the ice merely paused it. But others see a deeper pattern, because throughout Earth's history there's a rhythm to invention. Big changes often follow big disturbances, the rise of oxygen, the Permian extinction, the impact at the end of the Cretaceous, and yes, perhaps the Snowball Earth events. They shake the board, force new moves, and when the pieces settle again, life looks different. So what have we learned from all this deep science? We've learned that rocks remember, that chemistry speaks in ratios and whispers, that time is etched into crystals, that climate once modelled reveals its tipping points, and that life, even in silence, finds ways to listen, to wait, to survive. Beneath the quiet narration of data, there's a story that pulses, a story of balance lost and found, of thresholds crossed, of complexity rising from collapse. And it's not over, because the more we understand Snowball Earth, the more we realise that the planet is not fixed. It breathes, it experiments, it forgets, and sometimes it freezes. And yet, again and again, it thaws. When the last Snowball Earth melted, the world didn't rush back into balance. It stumbled, like a patient waking from a coma, disoriented, fragile, unsure of the room around it. The ice had vanished in a geological blink, but the systems it had paralysed took far longer to remember how to function. Oceans, for instance, didn't simply return to their old rhythms. For tens of millions of years they had been sealed tight, low in oxygen, stratified like forgotten soup. The upper layers had frozen, the deep waters had gone still, and now, with the cap broken, the oceans gasped, but their breath was uneven. The first great surge came with the melt, not just water, but nutrients. As glaciers retreated across the continents, they released a slurry of minerals, phosphorus, iron, silica. These elements, locked away beneath the ice, now poured into the seas, fertilising the surface and feeding ancient plankton. The result? A bloom. Phytoplankton, those tiny sunlight-hungry cells, awakened and multiplied. They spread across the oceans like a tide of green lace, and in doing so, they altered the chemistry of the world again. Photosynthesis consumed carbon dioxide and released oxygen. Dead cells sank, carrying carbon to the seafloor. A biological pump had restarted. The air grew richer. The ocean slowly began to turn over, but it wasn't immediate. Oxygen took time to diffuse. Stratification lingered in places, and in the deepest zones, hydrogen sulfide, poisonous, corrosive, still lingered like a ghost in the current. One breath in, one breath out. Over thousands of years, the ocean began to stir, and in that stirring, ecosystems began to form again. First came the microbial mats, layered colonies of bacteria and archaea. They carpeted the seafloor, built domes and ridges, created oxygen oases in a largely anoxic world. Next came the algae, larger, more complex, more demanding. They thrived in the light, absorbed nutrients and shaded the waters green. And then, something new. Not just single cells clumping together, but coordination, specialization, communication, multicellularity. We often think of complexity as inevitable, as the natural direction of evolution. But it's not. Complexity is expensive. It requires energy, oxygen, space. And for much of life's history, those ingredients were in short supply. After Snowball Earth, they arrived in abundance. Oxygen, rising slowly, allowed cells to breathe more efficiently. Nutrients, flushed into the ocean by retreating glaciers, supported denser food webs. And in this open niche, this post-glacial emptiness, life began to build upwards. Sponges, soft-bodied worms, creatures with mouths, guts, movement. Some of the earliest hints come from the Dushantuo Formation in China, a sedimentary archive of post-Marinoan life. Under microscopes, researchers found microfossils resembling early animal embryos, dividing in regular patterns. Others discovered strange tubular organisms with differentiated tissues. Not quite animals as we know them, but close. These forms, emerging only millions of years after the thaw, suggest that the evolutionary fuse had already been lit, perhaps even before the ice. But now the flame had space to burn. Meanwhile, across what is now Australia, Namibia, Newfoundland and Russia, the Ediacaran biota began to bloom. They were strange. Quilted fronds anchored to the seafloor, circular discs with radial grooves, ladder-like forms crawling slowly across microbial carpets. Some resembled giant feathers, others looked like giant leaves. Few had mouths, none had skeletons, and they leave behind no descendants, at least none we can clearly trace. But they were large, organised, multicellular. They filled the newly oxygenated world with new shapes, and though they would vanish before the Cambrian explosion, they mark a turning point. Life no longer just surviving, but exploring. And it wasn't only biology that changed. The landscape itself bore the mark of the long freeze. Where glaciers had scraped, they left U-shaped valleys and shattered peaks. Where they'd melted, they carved braided rivers and floodplains. The sea levels, which had dropped drastically during the Ice Age, now surged back. Coastlines redrew themselves. Shelves flooded. Habitats expanded. This new geography shaped evolution too. Shallow seas over continental margins became breeding grounds for diversity. They were warm, lit, nutrient-rich, a perfect incubator for experimentation. And beneath all this, Earth's internal engine kept turning. The supercontinent Rodinia, already breaking apart during the Cryogenian, continued to fragment. New oceans opened. New mountain ranges rose. Tectonic plates shifted and ground, driving volcanism, weathering and further climate feedbacks. This constant motion, combined with post-glacial recovery, set the stage for the next major act in life's story, the Cambrian explosion. But it didn't happen overnight. Between the end of Snowball Earth and the burst of animal diversity lay about 100 million years of slow, steady change. A long exhale, a planetary recovery, step by patient step. And this interlude, the Ediacaran period, is often overlooked. No dinosaurs, no teeth, no forests. But it was during this time that oxygen levels rose to near modern levels, that carbon cycling stabilised, that ecosystems began to differentiate, that genetics got braver. Genomic studies suggest that the genes responsible for body plans, for segmentation, for bilateral symmetry, all began to evolve here. Not in a rush, but in whispers. The world was recovering, but also preparing. So what were the long-term consequences of Snowball Earth? First, it likely reset the evolutionary playing field. Whatever biospheres existed before the glaciations were dramatically reduced. Many lineages may have gone extinct. Others were bottlenecked, reduced to small, isolated populations, and that genetic winnowing followed by post-glacial expansion may have accelerated innovation. Second, it reshaped Earth's climate systems. The weathering of post-glacial landscapes pulled CO2 back down, stabilising the greenhouse effect. Oceans mixed, nutrients recycled. Cloud formation patterns shifted with the new geography. Earth emerged more balanced, not immune to future swings, but buffered. Third, it may have altered Earth's redox state, the balance of oxidation and reduction in oceans and atmosphere. This influenced which elements were bioavailable, which chemical reactions dominated, and which metabolic strategies were favoured. In short, it rewrote the rules of the biogeochemical game. And fourth, it left scars we can still read, not just in rocks, but in cells, in the deep history written into DNA. Many of the genes that govern stress response, environmental sensing, metabolic flexibility, they likely trace back to these extreme periods. And perhaps, most importantly, it reminds us that change, deep, structural, uncomfortable change, can lead to unexpected beauty. The Earth nearly froze itself into silence, and from that silence came complexity. It's a strange comfort, really, because we live now in a different kind of transition, not glacial, but rapid, not driven by weathering or volcanic cycles, but by us, by engines and emissions and altered skies. And while Snowball Earth is not a map for our future, it is a kind of mirror. It shows what happens when feedbacks spiral, when carbon tips a system, when ecosystems strain. It shows that recovery is possible, but slow, uneven, unpredictable, and it shows that life, even when pushed to the very edge, finds a way to become something new. Snowball Earth was not the end. It was a chapter, a strange, frozen, silent chapter. But the one that came after, full of colour and limbs and nerves and questions, that's the one we're still living in. And it all began with ice. Sometimes, the more we learn about Earth's past, the more we realise how little of it is truly past. The Snowball Earth isn't just a story buried in ancient stone. It's a reflection in a dim mirror. Because while the glaciers of the Cryogenian have long since vanished, their echoes move quietly through our present. Not in ice, necessarily, but in pattern, in vulnerability, in the simple reminder that balance is something borrowed, not owned. And maybe that's where this becomes more than history. When we imagine a planet locked in ice, we think of it as foreign, alien, disconnected from our lives of cities, satellites, and search engines. But Snowball Earth isn't a fable, it's a fact. And it teaches us something simple and unsettling. The Earth is not fixed. It's not stable by default. It's reactive, dynamic, and deeply sensitive to the chemistry of its own skin. During the Cryogenian, the planet slipped into a spiral not because of a single disaster, but because of subtle shifts, tiny tugs in a long feedback loop, carbon dioxide falling, ice growing, sunlight bouncing. A few degrees here, a few parts per million there, and then a tipping point. The loop feeds itself. The world becomes something else. And today we're feeding the same kind of loops, just in reverse. Instead of losing CO2 to weathering, we're pouring it in. Billions of tons every year, unlocked from fossil archives and pushed skyward. The greenhouse effect, once too weak to keep the tropics warm, now builds strength. The atmosphere thickens, heat lingers, glaciers retreat, and though the direction is different, the principle is the same. Change the chemistry, and the system moves, slowly and then all at once. Snowball Earth reminds us that climate is not just about temperature, it's about balance, about interconnected systems tipping together. When one changes, the others follow. Sea ice expands or melts. Ocean currents slow or shift. Rain patterns change. Ecosystems falter. And feedbacks emerge from the noise. But perhaps the most haunting part is the timescale. Because when Earth froze, it didn't recover in a season, or a century, or even 1,000,000 years. The CO2 that built up through volcanic outgassing, enough to trigger a global thaw, took tens of millions of years to accumulate. The carbon cycle runs slowly, like an old clock in a quiet room. It has no sense of hurry, no panic button, just reaction, over time. Today we're reversing that process in a geological instant. What took nature millions of years to adjust, we are shifting in a century. The same carbon that was once drawn slowly from the air by chemical weathering and buried in stone, we're now unlocking and burning at a pace that no natural system can match. It's not that the Earth can't respond, it's that it can't respond fast enough. And that delay, that slowness, is what makes modern climate change both dangerous and deceptive. Because everything feels fine until it doesn't. Because systems don't collapse in obvious ways. They bend, they creak, and then, somewhere quietly, they snap. We know from Snowball Earth that abrupt transitions are possible, that ice can spread quickly once a threshold is crossed, that oceans can go anoxic, that ecosystems can vanish in the silence. And we also know that recovery, when it does come, is not always gentle. The Earth does not return to its old self. It becomes something new, a different balance, a different configuration. And life must either adapt or yield. This isn't to say we're heading for another Snowball Earth. We're not. The planet is warming, not cooling. But we are pushing the system, and every push, every emission, every cleared forest, every melted glacier ripples through the web. We're learning slowly that the biosphere is not an ornament, it's a regulator. Forests draw carbon, oceans buffer heat, wetlands store floodwaters. When we disturb them, we disturb the very systems that keep us comfortable. And yet, Snowball Earth offers more than just a warning. It offers a kind of hope. Not the cheap kind, the kind built from slogans and denial, but a deeper kind. The kind rooted in resilience. Because what Snowball Earth really proves is that life can endure almost anything. Darkness, cold, starvation, poison. Somehow, amid the worst freeze the world has ever known, life held on. Not everywhere, not easily, but enough. And when the thaw came, life did not just return. It blossomed, it grew bolder, more complex, more connected. Adversity didn't just test the biosphere, it shaped it. That resilience is part of our inheritance. The mitochondria in your cells, the organelles that power your breath, your heartbeat, your thought, descend from ancient symbioses born in oceans touched by glaciation. The genes that guide your development, your healing, your senses, they carry the fingerprints of deep time survival. And maybe that's the quiet comfort in all of this. We come from survivors. Our ancestors, biological and geological, lived through catastrophes. Not because they were strong, but because they were adaptable. They found niches. They waited. They changed. And we, in turn, carry that same capacity, not just to endure, but to respond. Today, we face a crisis not of cold, but of heat. Not of ice, but of acceleration. And unlike the cyanobacteria and algae that face the cryogenian, we know what's happening. We can measure it, model it, prepare for it. We can learn from the past, not to repeat it, but to outgrow it. We know now what tipping points are. We know what happens when feedback loops gain momentum, and we know, painfully, how fragile systems are. Coral reefs, monsoon patterns, polar ice. But we also know that action matters. The cryogenian didn't have solar panels. It didn't have conservation plans. It didn't have a species capable of predicting its own impact. We do, and maybe that's the real lesson from Snowball Earth. Not just that change is possible, but that intervention is too. That we live in a narrow window, a fragile equilibrium, but one we can protect, or break. That we are part of the system, not separate from it, not above it. And so, when we look at the great freezes of the past, we don't see fate, we see instruction. An ancient world frozen in time, whispering across the eons, understand your planet, respect its feedbacks. Don't mistake the present for permanent. Don't assume balance is forever. But also, if the world can survive 100 million years under ice, maybe it can survive us too, if we let it. And perhaps that's the most radical thing we can do, not conquer the Earth, but collaborate with it. To stop treating nature as a backdrop and start recognizing it as a partner. One that speaks in cycles, in patterns, in consequences. The Earth is not ours to command, but it is ours to care for. And care, like climate, is cumulative. So as we drift through this present moment, this delicate chapter between storm and stillness, we carry both the weight and the wonder of that history. We are not its victims, nor its masters, just its stewards, brief passengers on a long, improbable journey. The same journey that once passed through a frozen, silent, icy world, and came out somehow, on the other side, warmer, wiser, full of colour. So now we find ourselves at the end of a very long drift, from ancient glaciers to deep-sea microbes, from isotopes to embryos, from ice to imagination. We've wandered together through a world that once froze itself silent and somehow thawed into something new. Maybe you're lying down now under a blanket, or maybe you're just pausing somewhere quiet. Either way, thank you for staying, for following the trail of the coldest chapter in Earth's long story, and for letting it unfold slowly, gently, one breath at a time. If you find comfort in these stories, in deep time, in soft voices, in the wonder of what came before, feel free to subscribe or share this with someone who might need a little calm tonight. And if you'd like, leave a comment, tell me where you're listening from, or what the stars look like where you are, or whether you've ever stood on a glacier and felt its breath move past you. I read every word, and they help shape the next steps of this journey. Next time on Just About Earth, we'll drift into something new. Maybe mass extinctions, or ancient forests, or the quiet secrets of volcanoes. Whatever it is, we'll take it slow, but for now, close your eyes if you haven't already. The ice has melted, the ocean is waking, the sun is rising over a world made strange by time and beautiful by survival. Rest well, traveller. You're part of a planet that remembers and forgets and begins again. Good night.